Welcome back. We are starting the second course of the school, and the lecturer is Kenta Hotokezaka from Princeton. He's an expert on numerical simulations of compact binaries, and in particular their electromagnetic signatures. And this is what this course is going to be. So, Kenta.
Okay, can you hear me? Yes. So, thank you very much for inviting me this summer school. So, I'm planning to give lectures on basic physics of EM counterparts. So the plan will be, first I will discuss basic of kilonova. Probably you have heard, everybody have heard about kilonova? Yes? Somebody haven't heard a kilonova, this familiar? Okay. And the second, I will talk about the GRBs, which is gamma ray burst, which is high energy emission. And third, I will talk about afterglow. This is afterglow, which is known to follow the GRB gamma ray pulse, and after days, months, the afterglow follows this gamma ray pulse. So I will talk about theory of afterglow, and if I have enough time, I will talk a little bit more related topic. And today I will mainly discuss what is kilonova and the basic features. So first of all, let me introduce a brief idea of mass ejection and outflow from neutron star mergers, which produce the electromagnetic signature. So let me write down some pictures. So there are two neutron stars here, and which inspires in. And just at the moment of the merger, the tidal, we already discussed something about tidal interaction. The tidal force on the neutron star is too large, and some of the material here gets some disrupted. And then time goes on, it merges, and some this tail is ejected. So this is we call tidal ejector. Tidal. So probably both neutron star has a tidal ejector, something like this. So this is one mechanism that the binary neutron star ejects some material. And also, this inspiring neutron star has an approaching velocity here. So it's rotating, and at the same time, its orbit is shrinking so that they merge. And this approaching velocity about 0.1 c. So this approaching velocity is fast enough so that at the moment of this two neutron star collide, so this material of the neutron star around the surface suddenly feel strong compression. And this velocity actually the faster than the velocity sound speed of the neutron star surface material, so that it produces shock. Let me use, so here at the collision, you have some shocked material here. And you can imagine that you squash some, for example, orange to the wall, then you have this orange or a tomato, whatever you want, ejected in this way, right? Just squash this material here, and then which just breaks out from the interface. So this component, we usually say this component is shock ejector. So this is what usually we see in a numerical relativity simulation. When you simulate merger of two neutron stars, the tail of this material is ejected, and at the same time, you see the material ejected from the interface. So this is interesting because 10 years ago, we didn't see this component because just simulations are based on Newtonian. So in Newtonian gravity, the approaching velocity is very slow, and this compression is very weak. So what we saw in 10 years ago, the just tidal tail is ejected. But now we have a numerical relativity simulation, and then these relativistic neutron stars. So it's compact enough, and the approaching velocity is very fast, and this compression gives you the shocked material. So this sort of numerical relativity changed the picture. How much mass? Yes. So unfortunately, I cannot tell you how you can estimate how much mass is ejected, but as long as we see in numerical simulation, let's say, we call this is dynamical ejector, which is m tidal plus m shock. This is about 0.01 solar mass. So 1% of the solar mass is ejected. And of course, how much shock, how much tail depends on the mass ratio. If your mass ratio is strong, of course, if you can imagine this is neutron star, this is a black hole. There is no shocked material here, so just the dynamical mass ejection is just a tidal tail. But so in that sense, actually how much in the tidal tail and how much in the shock, it depends on the mass ratio. And more equal mass binary, we get more shocked material. And I would say in equal mass case, the somewhat comparable material we see in the simulations. Because, right, let's say, because neutron star, you know, if you go to the lower mass, then your neutron star has a little bit larger radius. And self-gravity is weaker because a little bit larger and a little bit low mass. So if you write down, for example, maybe you have heard about this Roche potential or something. Something like this. So this is a equipotential surface, and the material inside this potential is bound. And now we have, this is massive one, M1. And let's say this is M2. So this size shrinks if you go to the higher mass ratio, and the low mass neutron star easily fill this Roche lobe, and then outside the Roche lobe, this material is ejected. So if you go to the low mass, I mean high mass ratio binaries, it's easy to fill this Roche lobe by M2. So in that sense, and then go to equal mass, it's not so easy, so it's the reason. Yes. This is for GL and hydro. They still haven't talked about the lower magnetic field, but this time scale is fast enough, and then let me show you, introduce some idea of the time scale. So this mass ejection occurs the time scale of the orbital time scale of the neutron star merger, or some dynamical time of the neutron star merger. So the mass ejection occurs. So this is dynamical mass ejection, and here, let's say, T merge. You see something like this, and timescale is basically this mass ejection, let's say a few milliseconds. So this is very fast and few orbital time, so that probably just the interface, the magnetic field plays an important role, but just few orbit, you don't really generate the global magnetic field. And how much shocked material you expect is a bit tricky, and we don't really understood. Then we know for equation state, which has more smaller neutron stars, we have more shocked material. So in that sense, the amount is actually depends on the approaching velocity and how the compression is strong. But this is what we understood so far, and right, not very strong. And it also depends on the equation state. If you have a more compact equation state, I think this is not so dependent on the mass ratio. But if you go to the bigger neutron star, then tidal effect may be more stronger. Then you expect a little bit stronger dependence on the mass ratio. Yes. Velocity, yes, good point. I would say the mean velocity, is about 0.2 c. This is a typical velocity, but this is, we know from simulation, for example, you can plot something like this. It's a velocity and mass. We something like a mass of which velocity is larger than some value is something like this, and probably this is 0.1 c. It's almost continue to the close to the c, but the amount is very small. Typically, let's say this is 0.8. It's 10 to the minus 5 to 10 to the minus 6. So almost here, and this is 10 to the minus. Yes. Yes. This object or the remnant object? These two? You can put spins, but usually we don't use spin because usually the double neutron star spin down when it merges. The spin angular momentum is much smaller than the orbital angular momentum usually. So you can also think of this possibility of the spinning mergers, but typically numerical relativity simulations are done without spins. Yes. It's if you put a significant amount of angular momentum, yes. Initial data, what? For instance, we assume, for example, conformal flat metric and circular orbit. Yes, but yeah, if your neutron stars are separated enough, then it's more or less isolated. Sorry? No, it's for numerical simulation, we self-consistently solve the configuration of the binary. Yes. Kilonova emission is from both. Yes, now yes, I will, let me go further, yes. So now I have this configuration. So now we have looked at this problem from on the equatorial plane, but now we can see, so after the merger, now we have some central object, maybe black hole, maybe neutron star, and some material is created because this produced some mass ejection, but also some part of this ejection just not unbound, the fallbacks, which form this kind of accretion disk. And shocked material is more or less spherical, so we expect here sort of spherical distribution of the shocked ejector. And on the equatorial plane, we have this tidal ejector. And this is not the end of the story, so we have more mass ejection after the merger, which is coming from this accreting material. So this is accreting, and now magnetic field is very important because magnetic field acts like a viscosity, and then angular momentum transferred to the outer region and energy released at the inner region. So this energy, some part of the energy is carried away by some material outflowing from this. So this is we call, let's say, wind component. Typically, wind component is some epsilon, some efficiency times disk mass. And to figure out how large fraction of the disk is evaporated due to this accretion process, you need to do this massive numerical simulation with the MHD. And typically, so far people found this is about 10% to probably 50%. And from numerical relativity, we know how much accretion disk there. So M disk maybe up to 0.1 solar mass. Yes. How the angular momentum axis, oh sorry, yes, angular momentum axis is this way. It both, because after this mass ejection, not all the material is unbound. Some material is still bound and fallbacks. And shocked material also coming back, some of the shocked material coming back. And tidal tail also coming back. For the black hole neutron star merger, we have always a good relation between the M disk and M dynamical ejector because both processes dominated by just tidal tail. But for neutron star merger, it's hard to say because why? Because just merger. So for neutron star merger, we don't see good, beautiful relation between the disk mass and dynamical ejector. The main reason is after the merger, you have this is hypermassive neutron star. This is remnant neutron star. And you have some accretion disk around this. And because this is deformed, and some angular momentum and material is transferred to the disk. So after the merger, we still, for some small amount of time, but we still see some ejection. I mean, some amount of the mass is transferred to the disk. So this process increases the disk mass, and we don't have a good relation between the disk mass and dynamical ejecta. So that it's not very clear that which dominates, the dynamical mass ejection or disk mass. Numerical?
Are we considering more general backgrounds?
In numerical simulation, we consider
Spherically symmetric?
no, general. It's more dynamical. No, we may enforce the equatorial plane symmetry, but we don't enforce any symmetries.
Okay, then I'm fine.
So you can see, so dynamical ejecta mass depends on the mass relation equation of state, but probably up to 1% of the solar mass. And for the disk mass, because disk mass is up to 10% of the solar mass, of which about 10% to 50% can be ejected. And another complication is, of course, this remnant may launch something like some jet. So now I can summarize here. So this tidal tail and disk wind, so this component make kilonova. And this jet, probably it's a launcher jet, and then this GRB. Okay, the jet, the definition of the jet, okay, I didn't talk about the velocity. So typical velocity of the disk wind is about the escape velocity from the disk, which is wind is about 0.05c, 0.1c. Now, if I talk about the jet, then velocity is close to the c. And Lorentz factor is maybe 100. And probably this both, GRB and the kilonova ejecta, both may produce afterglow. So this is the picture that we are thinking. Definition? Why jet is formed? No, it's I didn't explain, and also it's not of the problem. Yes.
So the dynamical mass versus time is plotted there. So how long the t-axis can go, and what is the, like, why it is saturating? Like, it should go down after some time, right? Like, how, when it ends, that graph, like, so you draw that day, right? Like that graph.
Yes, this is just a
Dynamical mass.
dynamical mass is saturated at around
Till
10
what?
milliseconds.
Like it. So when till the simulation stops, it will be like a constant. I mean, why it's going like?
Integrated, yes. DMDT is something like this. Yeah. So, yes, and this one lasts longer, maybe 1 second, longer than 1 second. It's included, yes, sorry. Yeah, something like this. Yes. Okay, this is some sort of a picture that we are going to discuss. So, any more questions? So now this BRB and kilonova both probably generate own energy by own material. But for the afterglow, we are assuming this object is surrounded by the gas, interstellar medium, and hit this interstellar medium and release some energy. So this is about 10 kilometers here. And this maybe extend to 10 to the 7, let's say 100 to 1,000 kilometers. And these are unbound. So, but all this ejection process occurs around the central object. So this processes occur about 10 to the 7 centimeter, and just they freely expand afterward. Okay. So this is the picture that we had before the discovery of GW7817. So, and what we saw after this nice, by the way, this is almost 1 year. So during this week, we will celebrate 1 year after this discovery. Anyway, so after this gravitational wave event occurred, and then LIGO alert when and where this merger happened, and everybody were looking for this counterpart. Then what happened is this is luminosity. So first, the optical and the infrared telescopes found the first signal, which was about 0.5 days after the merger. This is time since merger. So here's the first detection. And the luminosity was about 10 to 42 erg per second. And since after the merger, this luminosity declined. So this is, say, 10 day. And this is 100th day. Here, maybe today. So it declines something like this. And I believe the last detection in infrared was about 70 days. This is the last point. Last time we saw the kilonova. Afterward, it's too faint to see. And probably this is 10 to the 39 L per second. So we didn't really see rise up. We just see some peak luminosity here, 10 to the 42 erg per second, which is a little bit fainter than supernova. Maybe 10 times fainter than supernova. And just it continuously decline. And from 0.5 days, about 1 day to 70 days, it just decreases by 2 orders of magnitude. 70. 70. Yeah, so most of the optical telescope couldn't see this object after maybe 1 month. And only Spitzer telescope was able to see. So there are 2 infrared detection points, 45 days and then 70 days. Right. This is a sort of model-dependent argument, because we know at 70 days we have radio detections. And from radio detection, we can extrapolate how afterglow bright in infrared. And it really bit, maybe factor of 10 fainter than the detection. So that is why we think this is a tail of kilonova. So this is what we see in terms of luminosity. And we can also write down this kind of figure. For example, temperature. Say here it's 10 day. Here it's 0.5 day. So temperature initially 10,000 Kelvin, and at 10 days, after 10 days, it was like 1,000 Kelvin, which also just decreases with time. And after 10 days, we don't have good photometric data. I mean, we have only few flux at a given wavelength, so we can't really tell you what is the temperature, but it's roughly speaking 10 to the 4 to 10 to the 3 kelvins. And then it's just from decline from blue to red. And yes, this is basically, this is just argument. The luminosity. So yeah, I would say this is effective temperature. So yeah, effective temperature. It's better to. Oh yes, it's the yes. So first of all, you have to fit data with a black body spectrum to estimate the temperature, and then you also get this radius r. And this is 10 to the, what is the scale? Yes. So I'm not sure you are familiar with this unit. But at one day, it's already, the size is about 10,000 times bigger than the solar radius. So which is, how much is it? 10 to the 15 centimeter. So it's already bigger than the Earth orbit, right? 10 to the 15 centimeter. This scale is, what we see is this ejector. And what we see is some emission from the ejector, and there is some photosphere inside the ejector here. So we are seeing this photospheric radius. You're saying GRB spectrum? Right, GRB spectrum is very different from black body. But this one is not so different from black body. And if you look at the spectral measurement at one day, few days after the merger, it's very, very beautiful black body. You can see this. This is actually surprising that from a theoretical point of view, it should a little bit deviate from black body, but it's very look like black body. And after 1 week, it's deviate from black body because of atomic structures. But still, you can sort of estimate where is the most, what wavelengths we see most of the photon. So in that sense, you can sort of define the temperature. Yeah, from first of all, you need to measure effect, and you have observation. Then you get the radius. First, so I write down this is Okay, yes. Actual observation is not just luminosity, but luminosity as a function of the wavelength. So you can get sort of the idea of the temperature. Yes.
So before 0.5 days, do you expect to see a rise and have a peak and then?
Yes.
So in the UV.
Yes.
So if an UV optical monitor wants to monitor, how soon should they start, or how later can they wait?
That is what I'm going to tell you. So please wait a second. Now from this, this expansion, actually you definitely see some expansion. So that this is not like a cloud around the neutron star. This is expanding. So it's something ejected from the system, and velocity from this photospheric velocity is about, let's say, 0.1 to 0.3 C. So this is observation. So it's sort of agree with the picture that we had here. Yes, this is just the radius, time derivative of this radius. Which one? This one? This photosphere? This is changing, yes. This is early time. So at one day, it's about 0.3 C, and it decreases to about 0.1 C. Yeah. Yes. So why we see slower material? Because the photosphere is not always at fixed velocity. It's shrinking toward inside after some expansion. So initially you see faster material, and after density drops, then we start to see more inside, so that we see the decreasing photospheric velocity. Yes. Yes, yes. Okay. More questions? So now we want to understand from this observation. So just we can immediately tell, this observation immediately tell us that it's expanding, and velocity is about 0.1, 0.3 C. But now we want to calculate more. Yes, you're right. We expect some, this variety of mass ejection. We expect some variation, but what we see is just time evolution of the flux as a function of wavelengths. It's not very easy to map from this information to, so it's sort of ambiguity there. So these are just what we can really say from the observation. But from here to here, it's sort of, you need some model and then. The early time is quite look like a single black body. And late time is not like really black body, but some absorption lines, absorption features that we can't really fit the black body. Yes. Yes, so she's asking, we expect a different type of emission. But as long as look at the light curve, if you have definitely two different components, what you expect is two bumps here. One from one component and another one from another component. But in the total luminosity, we didn't see such two bumps. So what we see is just tonically declining light curve. So it's not very clear that two components, single component, three components. So it's still, just look at the observation. It's not really clear. So, yeah, motivated by these observations and the theory, the model that we discussed, we want to calculate something this kind of problem. So I simplified maybe more than you expected. So I have some gas, spherical, uniform density, expanding V. And let's say this R and V, and the mass M. So what I want to do, what I want to know is how the internal energy or thermal energy of this gas changes with time. So given this situation, I want to solve this thermal energy of the expanding gas. So because I want to solve this, so what I have to do is look at the energy conservation. The change in the internal energy, also I assume here, the internal energy is smaller than the kinetic energy of the expanding gas, so that we can assume the V is constant with time. If this is not true, the gas is accelerated, so V changes with time. But for now, we assume this situation, and under this very simplified situation, we can discuss how light curve look like. So delta E, as we know, this is from thermodynamics, right? This looks familiar, right? So your energy change is just heating or cooling for your system, and if it expands, it's cooled down because this internal energy works the gas. So now, for simplicity, we just look at this problem. If there's no entropy change, then just we want to solve this problem. So this is the most simplified problem, what happened. So this is so the volume change, because we are now assuming the constant velocity, so it's just so changing with time, something like this. And the pressure, we know the equation of state, the ideal gas equation of state. The pressure related to the internal energy density with the adiabatic index. So now for our problem, because this is full of radiation, the adiabatic index of our problem is, we can assume the gamma is 4/3. So then this equation becomes and you find the solution should be equals like 1/T. So this is a very simple, the easiest calculation probably you have done somewhere, maybe in cosmology or something. Just if you have an expanding material with constant velocity, due to this expansion, the photons filled in this gas works the expanding gas and lose its energy. So even though the number of photons inside the gas is constant, but the temperature decreases goes like 1/T. So this is the effect of adiabatic cooling. We call this is adiabatic cooling. Even though there is no heat up, cool down, we have some cooling of the photon. So this is adiabatic cooling. But now, this is not the situation because it's by definition we see the photons escaping from the system. So there should be some photon escape from the system, which should be included in this term. So let's include this term. So second simplified version is just cooling minus the radiation luminosity. So this is just how much energy escape from this system, which is something like this. Minus, so we know now this adiabatic cooling term, 1 over T. So now the question is, how we can calculate the radiation luminosity. So now let's imagine so let's assume the gas is not completely optically thin. So photon, let's imagine one photon emitted at center, propagate some length and scattered by some material composed of the gas, and scattered, and scattered, scattered, and after some random work, it escaped. So the photon, because of this random work, it takes some time for photons to escape from the system. How long does it take? So the time scale of this escape, so we call diffuse out, but let's call it radiation time. This is how long does it take for photon diffuse out from this expanding material at the radius r. So this is number of scattering. Oh, sorry, this is. So this is just we know each. So between the scattering, typically the photon goes like mean free path. Let's say mean free path. And it takes mean free path divided by c. And then it goes n scattering. So this is simply the photon escape with this time scale. And let me define that this is mean free path of the photon, which is the cross section times number density of the scattering particles. And we usually use, this is cross section and density. We often use this notation, kappa and rho. So this is, let's say, this is cross section. Let me define just, this is number density. So the mean free path is just length. So now kappa is, we call this is opacity. So kappa is a cross-section per unit mass. And this is density, just mass density. And just I give you some value. So kappa for the electron scattering is so opacity of the electron scattering. Someone knows the value? 0.4, yes. So this is just Thomson scattering cross section divided by proton mass. This is the electron scattering opacity. So it depends on what material you consider. This opacity changes, but not really much. It's maybe up to 10, 100, and maybe it's smaller than 0.1, but not like many orders of magnitude difference. And also from just this fact that the photon random works in this material, we know how many scattering the photon has. This is so n scatter is just right, this is the very simple, just you can calculate how many times the photon can scatter before the escape. This is the size of the system divided by mean free path squared. And then sometimes we call this is optical depth, tau square. So tau is, this is also important quantity, optical depth, which is, what is this? Sigma nr, or kappa rho r. So at a given radius, you can define the optical depth with given opacity, density, and the radius of the side. So now we can calculate the radiation time is this one. Square. So number of scattering times the time that between each scattering. So this is simply mean free path r, c divided by r. So the photon in this dense material takes, this is just the light crossing time of this expanding gas. If there is no scattering, the photon just escapes with this time r over c, but it takes more extra time because of the scattering, which is tau. So in this limit that photon scattered many times, we can, this is dt. We can use this dE dt minus E over t minus because the energy, internal energy escapes from the system time scale of T radiation. So this is like I want to solve if there is only the cooling term. And T radiation is kappa rho r. Sorry. Yes. Right. Rho r squared divided by c. And rho is, so this can be let's say r cube. So this is rho, half square. So this is cancelled. This is and I define here. So the radiation time will be shorter and shorter if your material expands, because initially it's too dense. The mean free path of photons is too small, so the photons don't have a chance to escape. But it's expand, it can escape. So radiation time decreases with time. And we define here the diffusion time square divided by T. So T diffusion time. Here, V times C, T, velocity of the expanding ejector. So this time scale is characteristic time of this expanding material. So at this time, T diffusion time, photons can escape in one dynamical time scale. So after this time scale, photons easily escape, but before this time scale, the diffusion time is much longer than the dynamical time. So now this equation is minus E minus T let's see. You can solve this differential equation. So the answer is the solution is yeah, let's take time t0. This is initial time of this explosion, t0. Maybe just the velocity, the initial size of the object divided by velocity. And this is the initial internal energy. This is how the internal energy evolves with time. So this term just shows the internal energy at T is suppressed by time T because of the adiabatic expansion. And after T diffusion, it exponentially loses the internal energy because of photon diffusion. This is a adiabatic cooling term, and this is a radiative cooling effect. So this is and if we want to know what is the luminosity from this object, so by definition, we define this is so this is radiation luminosity. You can just divide this E by T radiation, then you get the luminosity. In this case, it's a very simple case. It's just luminosity is constant up to about the diffusion time scale, and then exponentially decreases. So up to here is just without any assumption of the heating, but actually the system has heating. And you can estimate for the neutron star merger. Let's calculate this one. So given ejector mass and opacity and velocity, you can, yes. Which one? This one? The last one is L. E of t divided by, which is this one. Okay. Yes. Yes. Yes, 0.0. So from this, we haven't discussed how much mass is ejected and what is opacity, but we know some idea about the expansion velocity, which is about 0.2 c. And let's take the mass now for the mass 0.01 solar mass and opacity of 0.1, which is usually we assume in a supernova calculation. You get about half day after the merger. The diffusion time is about half day the merger. So if we look at this equation, so the luminosity is just the initial thermal energy of this ejector divided by diffusion time, and one extra factor, the initial time scale, which is maybe millisecond, 10 millisecond divided by diffusion time. So actually this suppression, adiabatic cooling suppression is very, very strong. So you can check in tutorial, you can check this, what is this luminosity compared to this luminosity, and then you may see this luminosity is far fainter than the luminosity that we see. So now, let's add this equation, the EDT minus, so this is what actually we want to solve, the diffusion square. Where? E naught. E naught, whatever you want. Maybe this is up to total mass B square. Yeah. But you can figure out what E naught you need to explain that's all. Yeah. So you can also solve this equation with some additional heat to this ejector. So we usually think for this kilonova, the standard model, we assume this is radioactive heating of the process elements. But you can add anything you want. Maybe you have your black hole radiates something, and the heat up ejector also comes to this term. And magnetar model, cocoon emission model, you can always assume some Q dot. And the solution is So let's say this is E. Yeah. This term, this is just depends on the initial condition. So this is let's write ET plus yes. By this is just formal expression by. Yes, now this is a general solution of our problem. So this is just determined by initial condition. And this term is determined by the additional heating. The function maybe you want to put in is radioactive heating or something else. So you can see, so this effect is just the heat that generated much before time doesn't really contribute to the luminosity. This is this factor. And also this is, oh sorry, this is energy, yes. This is adiabatic cooling, and again, this is radiative cooling. So you can also get the LT, the same procedure, ET, divided by the radiation. And in the end, what you get so this one, maybe something like this. So here is and then you have this additional term. Maybe you want to put the exponential for the nickel heating or some power law heating, but you can get something. This is usually rise up to some T diffusion time, and afterward, oops. Decrease this. And actually, this calculation is not really valid after the diffusion time, because the assumption of this simplified assumption doesn't work. But in the end, much after the diffusion time, the luminosity is about the total heating rate. Just the photons deposited to the ejector immediately radiated away. The luminosity is about heating rate. And the peak is around this characteristic time scale, which is calculated here. This is just this term. Oh, sorry, this one. Radiative. Second one is this one. This is heating, adiabatic cooling, radiative cooling. So all the combination. So this, some rise up. So for the kilonova, so the heating rate of the kilonova, I will talk on that topic tomorrow, but now, what you usually do is the heating rate is mass of the ejector times specific heating rate of our process. Oh yes, T0. What is T0? This is sort of arbitrary, but if you specify your problem, for example, I can say this ejector is produced at the margin at the radius of R0, which is 10 to the 7 centimeter. And because then the expansion time at this is already V, so T0 is about R0 divided by V. And E0, you can see how much internal energy that initially this gas has. It's up to the kinetic energy. So this is sort of discussed argument that how you specify the E0 and T0. But of course, you can assume something after this gas expands. At some point, something faster collides to this ejector, then inject more energy at some larger radius than R0. Then you redo this calculation, I mean. Yeah. Mm-hmm. Yeah. This calculation valid for Newtonian. You can't really do this relativistic calculation, but you can still think of some, faster than V, but still not extremely relativistic. Yeah. Mm-hmm. No, what I'm saying is at some bigger radius, you may consider some energy injection by the outflow that produced after the mass ejection. And this is not necessarily close to C. Yes, I don't have much time, but so this is the topic in tomorrow, but the specific heating rate of this R-process material, this is erg per second per gram, is about 0.3 10 to the 10. So this is this unit, 1 day. So this is sort of a power law function that, and you can put this time scale, this heating rate to the Q dot, and then, as we discussed, the peak time is more or less this time scale, and luminosity is the total heating rate at the peak time scale. So the peak T equal T diffusion time is you can calculate this 2 times this is okay. This is m q dot. Oh, sorry. I will talk about this. This is not completely phenomenology. This is based on, you can derive, I will show the derivation of this from theory of beta decay. So this is a little bit lower, fainter than this 40 per second, but given this uncertainties, and you can a little bit increase the mass. And this is, and you can get sort of a consistent luminosity. And also you can calculate temperature from just this description. At the peak, then effective temperature is about 7,000 K. Okay, so these are what we can learn from very roughly from this observation. If you have a peak luminosity and peak temperature and peak time, then you can do this calculation. Peak time should be the diffusion time scale you can estimate. So mass cannot be much bigger than 0.01. And the velocities cannot be much lower than that velocity. And then, given heating rate, you can calculate, you can estimate what is the required mass to estimate to reproduce this luminosity and also the temperature. So, and the next lecture will be more focused on this. What is this? How you can get this heating rate. And this is also the shape of the light curve is basically determined by the shape of the heating rate. So we will discuss this topic tomorrow. So, any questions? Yes. In this calculation.
So in the ejector, when you're talking about the ejector, tidal ejector, wind ejector, and shock ejector, you mentioned something about the magnetic field.
Mm-hmm.
So what role does the magnetic field play and how does it come into effect?
The magnetic field plays a role when you think of the accretion disk. If you want how much matter accrete on a black hole or central object, how fast, how much, and how much fraction will be ejected. In order to calculate this fraction or these properties, you need magnetic field. But once this the amount of the ejector from the accretion disk and the velocity profile are obtained, you can do this calculation. So the magnetic field plays a role for the initial condition of this calculation, this luminosity business.
You can't use the ideal fluid equation of state, right? For the magnetic field. You'll have some viscosity or... So your pressure is equal to gamma minus 1 E by V. That assumption would have to change if you have a magnetic field.
If the magnetic field is very, very strongly magnetized, yes. Then I think in that case, you wouldn't get Newtonian outflow. Yeah.
So, Kenta?
Yes.
So, so this solution is valid for any heating rate. So, at much later time, when we see radio afterglows, those we will include the Q dot from the shock into the interstellar, and this still works. Is it something like that?
Say that again.
So at much later time in the radio afterglows, when the ejector material is being shocked by the interstellar medium, then that Q dot comes from there and then still gives you luminosity in radio.
Oh. Okay. you're asking the later time, you can specify this Q dot
Yeah.
from the shock heating.
Yeah.
Yes. Yes. But yes. Okay.
I guess there will be an overlap between this radioactive heating and this and the shocked.
Yes.
But
yes.
I guess
Yes. Yes. Yeah. You can do it, but then you have to be very careful. You can't put the shock heating, just the shock heating here.
yeah, it's non-linear because
This is what we always not. We just assume these are internal energy in the photons.
yeah, like an isolated system, but then
So-
it's not isolated.
In a shock model, you need to specify the photon production by the shock. Then you get the, I think. But anyway, you get this Q dot to the photons is equal to the radiation.
And we also have to include maybe larger material, and then the Q dot will be like an isolated
yeah.
system, like a heating in the isolated system. Thanks.
Yes.
Are interacting with the material. So, but if you, I mean, I don't know what is the energy level of that photon, but if you consider the high energy photon, for instance, mega electron volt, then the, photon can interact with each other and that can produce, electron positron pair.
Mm-hmm.
So, should we, consider in this? I don't know.
No, we haven't considered this process. In this process, what we think is just thermal photons, which temperature is in optical and UV optical, maybe up to X-ray. But in order to calculate actually this heating rate, this one, it involves the radioactivity, so involves MEV gamma rays and electron positron creation. So then we will think this process tomorrow, but it's included in the Q dot.
Thank you.
Further questions? Let's thank both the speakers for this wonderful kickoff of the semester.